So, chemical kinetics, the first topic of Chem 2. This is something that you really never address in any of the other chemistry classes you take before this. You've seen it, because chemical kinetics is really about the rates of reaction. So you've seen reactions that were really fast, you've seen reactions that were really slow, ones that you have to set up and you wait for them to happen. There are other ones, like if you remember, do you guys all do the copper cycle lab? I know my Chem 20 did it in Chem 20, but you do it in Chem 1 also, right? When you dissolve that copper with the nitric acid, that's a fast reaction. But something like rust on iron happens really, really slowly. So chemical kinetics is how we define and understand and describe the rates of reactions. How fast do they go? And then that'll tie into the next chapter when we talk about equilibrium, because you've got this reaction rate that's going forward, making products, but some of those products, in a lot of reactions, can react again and then go back and become reactants. And you end up with this balance of two things flowing forward and backward. But we have to talk about kinetics first. So you probably know lizards are cold-blooded. They're ectotherms. So they don't generate enough heat internally. They need external sources of heat in order to keep moving. Part of the reason for that is because the rates of the reactions in their bodies, and in our bodies also, depend on temperature. So if they get too cold, those reaction rates slow down and can become so slow that they can't survive. So that heat, the temperature, speeds up those reactions. Same kind of thing if you get into like hypothermia. Reaction rates slow down too much. So chemical kinetics, study of rates, and then especially the ability to control those rates. So if we can understand and describe what the rates are, then we can make changes and see what affects the rate. So as we saw with the lizards, temperature can affect reaction rates, concentrations can affect reaction rates. You guys all know what I mean when I say rate, right? So how much of it gets converted per amount of time. And reaction rates can actually give us some really interesting insights into how reactions happen. So I can take it to another step and say, if I've got multiple reactants that go into this reaction, sometimes if you change one, it won't have any effect on the reaction rate. Sometimes if you change another, it'll have really large effects on the reaction rate. So it can give us insight into how those reactions happen also. All right, so rate of a chemical reaction is a measure of how fast we are making products or using reactants. So it's a little bit late to the game. I was trying to make a visual of this, but reaction with a fast rate. So we've got these two things on the sort of same clock. We can see that in the sort of 4 cycles of time for that top one, we convert basically everything over into the products. But for the reaction on the bottom, that happens at a slower rate. So as time goes forward, we have not everything converted in that same amount of time. So when we're talking about rates, we have to, to talk about what rates are a little bit more. It's like speed is your change in distance over a change in time. And when we say over, it is really because literally it's the change in distance divided by the change in time. So it's over it in the reaction or in the equation. And if you haven't seen it before, the triangle here is capital delta, which just means change in whatever comes next. So we can abbreviate that and say change in x divided by change in time. So for chemical reactions, what are we measuring the change of? One kind of molecule, one kind of atom into another. And how do we measure? Well, actually, so can we count the individual atoms and molecules? No. So what would be another way that we could measure the amounts of reactants? Molarity. Molarity is a good one. We do that all the time. We could also do, I guess in some cases, mass or pressure. But most of the time we'll be talking in terms of molarity. So when we're defining the rates of a reaction, in my mind, chemical reactions have always been almost like a series of gears, these things that are linked together. And if I want to turn one thing, convert one of my reactants into products, I have to also convert the other reactant into products. And then I have to also generate all of the products, right? So all of these things move together. If I use reactants, I'm making products. So when we define the rate of a reaction, there's actually a bunch of different ways that we can define it, and they're all related. So we have this overall, or getting a little ahead of myself, we define the rate in terms of just one of the reactants. So here in terms of hydrogen, which is decreasing because it's a reactant, it gets used up, concentration goes down, or pressure goes down. Another refresher, the brackets, meaning concentration of whatever's in the brackets. So this is saying this is negative because the amount of hydrogen, which is one of our reactants, is going to be decreasing over time. If we want to calculate that, we would say measure the concentration at T1, measure the concentration at T2, subtract those, right? How much did it decrease in how much time? So that defines the reaction in terms of one of our reactants. But like I was saying, these are all sort of locked together. So we could also define the reaction rate in terms of the products, right? If we can measure the product's concentration, then we can measure a concentration at time 1, measure it a little later, figure out what that rate is. Now increasing because it's in terms of our products, which concentration is going up over time. And here we add in this 1/2. That 1/2 gets added in partly because, well, I think what we're going to do next, is that on the next slide? We'll get there. We want to determine what the rate is for the overall reaction. So what is the rate that ties all of these together? We need the 1/2 because as I use up one hydrogen and one iodine, I make 2 hydrogen iodide, right? So that rate is going to increase twice as fast, or the concentration is going to increase twice as fast as the hydrogen or the iodine is going to decrease. So if I'm talking about, and really what we're talking about here is in not just a rate, but an overall rate for this whole reaction, I need to divide that hydrogen iodide concentration or rate by half. Again, because it's increasing faster, to relate it again to the overall rate of the reaction, we divide it by 1/2. And whatever that fraction that goes in there is always going to depend on the coefficient from the balanced chemical equation. So here we can see if we plot these things out as a function of time, there's a couple interesting things. And actually, it's kind of hard to see on the graph. But the hydrogen iodide concentration, which is the one that is increasing, of course, there we're going up. That's the hydrogen iodide, and the hydrogen's decreasing. The slope of this, or the amount that this increases over time, is steeper than the hydrogen decreasing, and it's twice as steep. At every single point, the hydrogen drops by some amount. The hydrogen iodide increases by double that amount, which makes sense. That's the balanced chemical equation. Let's see, I don't know, I guess the other interesting thing, though, is that those rates aren't constant. So it's not like, if this was a constant rate, then I would have one line that goes straight down, and then I have another line, red, that goes up. The slope would be twice as steep. slope of 2 instead of a slope of -1. Well, we can see that over time, the amount that the concentrations change by decreases. This is something that we'll look at a little bit more later when we talk about reaction orders. But we can just sort of briefly think about, well, why does that happen? Why does the rate slow down?
We have less
reactants. Yeah, because we're relying on, in presumably the balloon or bubble or vessel that this is reacting in, we're relying on those hydrogen and iodine atoms to collide with each other. And if they collide with enough energy, they react. But as we do that, as we use those up, as this concentration decreases, there's less and less hydrogen around, there's less and less iodine around, and it's just harder for them to find each other. And so there's less chance that they will react. And we could, I guess, if we wanted to, plot the iodine on there as well. Oh, actually, the other point to make here is there's a couple different ways that we can measure reaction rates. So here, we're measuring or calculating using these. Let me use a different color. There's a straight line here, which is tangent to that point in time. And unless you had a defined equation for this curve, in which case you wouldn't really need to do this, you can't really find the tangent without graphing. And as we'll see later, if we want to try and make a prediction, if we use this tangent at this single point, we can see that the rate changes over time because this curve is leveling out. It gets flatter and flatter. If I try to make some prediction forward in time to what the concentration would be based on this, the farther out we go, the more that line diverges from what is actually happening. So for a single point in time, this is really good for finding the rate. The other way that we can find the rate is by doing or calculating an average rate. So I should go down to this real quick. So these are calculating the average rate, where we're just taking two different points and we're essentially assuming a line between those points, and we're calculating the slope of that line. So if you rise over run, now we can see that. So this is the difference between, that's how much it decreased, the amount of time, 10 seconds. And this goes from 0.018 to 0.014 to 0.012, slows down over time. And just to illustrate, again, how we can't really make predictions with this, if I go on here and I draw a line from our initial, let's say for the hydrogen, let me use a different color. Or maybe it should be, oh yeah, blue. So if we start at our sort of initial time here, if I draw a line to any of these other points, we are at some point going to be, again, getting away from that straight, or what the actual curve is. So for average rates, they tell us something about that sort of period of time. But we can see that even under this whole area, that rate is changing as it goes through those, or it gets from point A to point B. So they're good estimations. We can use them to learn valuable information about these reactions. But I don't want to scare you. We're not going to use calculus, but we're going to use the integrated forms of rate laws to get much more accurate predictions of what the concentrations will be at future times. Because when we integrate these, they become straight lines. All right, so decreases. Oh, I guess I got to add myself a little bit again. So again, the instantaneous rate, let me highlight that because you should know the difference between the instantaneous rate is the rate at just one point in time. You pretty much need to graph it in order to calculate what that is. If this did come up as a test question, I would give you a graph. You do your best to draw lines, and there's going to be some error whenever you're calculating something from a graph. So use the tangent to find the slope just at that single point in time. All right, so this is the idea that all of the rates of the same chemical reaction are tied together, because as I use up reactants, I am producing products at specific ratios. And so if we generalize this rate for the, again, overall rate, if I can find that overall rate, or if I'm given that overall rate, then I can calculate the rate of change, at least the average rate of change, for any reactant or any product, as long as I have the balanced chemical equation. And you can see that these are all equals. Yep. Right? The overall rate is equal to each of these. So if you have one, you just set any two of those equal to each other and you can find the other. You don't actually have to calculate the overall rate. And as I was showing you on the graph, we can't make any predictions using this in terms of what the future rate is going to be, because what we're really doing is we're sort of drawing these straight lines on a curve. And so it is going to deviate from that curve pretty quickly. All right, so different chemical equation, a little bit more complicated. So this is actually the equation that you'll use in the lab next week. Well, actually, I don't know if you'll use the equation, but this is the reaction happening that makes the, if you've read it at all, when it turns blue, it's the triiodide species that reacts with the starch and turns blue. So if we want to calculate the average rate of this reaction, this is a key thing to, when you're reading a problem like this, even I assume on Alex, which I'll post the Alex homework for this week after today. Calculate the average rate of this reaction. It's not asking us for the average rate of iodide. It's asking for the average rate of the whole reaction, which means that we're really looking for the overall rate. So if we want to calculate the overall rate, all right, we do the generic 1 over A times the change in A divided by the change in time. Is this going to be positive or negative? Negative. Negative, yeah. Positively negative. So it's negative because we're calculating the rate for, or based on, actually, yeah, we're calculating the rate based on one of the reactants. So it'll be used up. So we put a negative sign in to the equation. So then 1 over lowercase a is the coefficient. And then the concentration, there's always, I mean, like other things, it's final minus initial. So the final concentration would be the 0.868 molar divided by 10.0 seconds. This ends up being getting ahead of myself. That's, you got to do this direction. So because there's a negative out front, this will be 0.0044 molar per second. Sorry, I was trying to think of an analogy. I don't think it quite works out. The rate here, and this is one of the places. One of the things I like about chemistry is you don't need to necessarily have this memorized. This equation even, right? If we know what we're trying to find, we want to know, well, what is the average rate for the overall reaction? Well, I can figure out how much the iodine changed in this period of time, 10 seconds. So it changed by, this down to this, so that's negative, over 10 seconds. So I can figure out this just from knowing how reaction rates are calculated. And I know that it's going to be negative. Well, this negative here even, like this comes out to be a negative number, right? Times a negative, so it ends up positive. Because I know iodine's decreasing, but if I want the overall rate, that's always going to be positive. How many molar per second is this reaction moving forward? Any questions? Yep. Okay. So moving forward, we're going to use this now. Determine the rate of change in the concentration of H plus during this time interval. So we want to look at concentration of H plus. And based on this slide alone, obviously there's not enough information, but this is part B. So continuing from the first one, the time interval is still 10 seconds. And now we know the overall rate is 0.0044 molar per second. Yeah. I just can't really ask. The answer's on the slide. You can kind of figure this out without doing any math. So I know the overall rate is. So if it has a coefficient of 1, the overall rate is the same as the rate of whatever species it is. So if we were asking about hydrogen peroxide, coefficient of 1, this rate will be the same as this, but it'll be negative because it's a reactant. Its concentration is decreasing. For the concentration of H plus, the coefficient is not 1, but it's 2. And so actually, if we set this up, we want to know what the rate of change of H plus in some amount of time is. But this is going to also have 1 over. I guess I can still use A, or we could say 1 over 2. Oh, and it's going to be, negative. So you can't do the algebra, but because it's got a coefficient of 2, I know that whatever the rate is for hydrogen, it's going to be twice the rate of the overall reaction. So if I know the overall, I can just multiply by 2. And if we do the math, this is one of those, I guess it's a situation where it really, really helps to understand what all of these variables are. And we actually get a little bit of a hint in the problem because I'm not solving for the change in hydrogen. I'm not solving for the change in time. I'm solving for the whole thing. So in a sense, we can think of this whole part as being X. And so let's just solve for X. Oh, sorry, there's a negative. And so if I want to get that 2 to the other side, multiply both sides by -2. I'll do it this way. So it's going to be -0.0088 equals x, which equals the rate of change of hydrogen in that same period of time. Units still molar per second. Still good? Any questions? Any at all?
Do you want to solve for just the change in nitrogen? You're just multiply that by right?
Yeah. So then since we know the time, we could plug the time in for delta T and solve for how much the hydrogen changed by. And then if we knew the initial hydrogen, we could figure out where it's at now. Or if we know where it's at now, we could figure out what the initial was. But only for, that same time interval. Otherwise, we really do need calculus. Rates of change. Cool. Yeah, good question. And actually, if you're trying to think about, so when I think about test questions, when I think about test questions from the perspective of having been a student, it was always a game. How many different ways could this question be written? If you have delta T, so I guess I just gave you a whole bunch of them that I could do. If I give you the hydrogen concentration at time after 10 seconds is this, what was the initial concentration? So that's where you plug the T in, you figure out how much it changed by to get back to the initial. Or I could give you the hydrogen concentration changed by this much. Here's the overall rate. How long did that take? I don't know if those questions are pedagogically useful. They're more like brain teasers at that point. Because we are kind of going to move on pretty quickly from this to get to the integrated rate laws. Right. So, actually not a huge fan of the way this question's worded. These are all slides from the first time that I taught Chem 2. So there will be updates made as we go. This is one that I didn't get to. So predict the rate of change in concentration of hydrogen peroxide and triiodide during this time interval. I don't like it because it says predict. Like, what we're doing is really like predicting what it is, but it didn't say that when we were doing hydrogen. It said determine, even though we're going to do exactly the same thing. Could just say find it. So now we know the overall rate. Again, we need that information. So what's the rate of change for hydrogen peroxide?
The
same as the overall rate, but negative. So for hydrogen peroxide, make it negative. I'll go through the whole. And for triiodide? Oh.
No.
Yeah. Because the iodide, iodide would be 3 times. Yeah. Triiodide is the product species. It would be the same, but positive. Or I guess, really, it is just the same. Missed a 0 there. And why are they the same, but different signs, maybe?
One's a reactive, what's a product? One is reducing with the tree.
Yeah, one's reducing, one's increasing, and they both have coefficients of 1. So the overall rate is really the rate of anything that has a coefficient of 1. Why do we do that? Because it makes it the easiest to translate to everything else. just a nice neutral starting point. All right, so for this general reaction, under a given set of conditions, we have a reaction rate or an initial rate of 0.1 molar per second. So what does the rate of change be? Yeah. So it's C because it's 2B. So it, again, most of the time when it says initial rate, if it doesn't tie it to a specific species in the reaction, it's talking about an overall rate. So like here, it just says the initial rate is this, but it doesn't say the initial rate of A or C or B. So then we can assume that it's the overall rate. And since that is 0.100 molar per second, you could do the math of 1 over 2, negative 1 over 2. So do the change of B over the change in time. And again, this is asking us really to solve for this whole expression, which you could swap out for X or whatever variable you prefer. Cool. So really the point being, if you can wrap your head around the coefficients and how they relate to the reaction rates, at least these average reaction rates, you don't really even need to do the math and write out all of the steps to convert to the rates of any individual species. Cool. So measuring reaction rates. Honestly, one of my favorite parts of chemistry is the actual instrumentation, like practical, like how do we do these things? How do we problem solve? And take more chemistry, you get to do more of that. For measuring reaction rates, we need instruments that can measure those rates. And there's kind of two ways to approach this. And really it has to do with how many data points do I need and how close together do they need to be able to see what the rate is. So for a reaction that's relatively quick, so something like less than an hour, you'll probably want to use some sort of continuous monitoring of the concentration so that you get enough data points. Otherwise, if you get the initial data point and the reaction finishes before you get your last data point, the reaction completes, then you just have a straight line rather than whatever the actual curve would be. For reactions that take place over a very long time, sampling the mixture at various times can be used. So actually, this relates to the research that I did. I did post-harvest fumigations, which means that you take all of the fruit that's been harvested and you put it in a chamber, and then you add gas that kills bugs. And that gas over time gets absorbed into the fruit or vegetables or whatever it is. And the concentration of the headspace or that's around the fruit decreases over time. Usually that's because it's being absorbed in. I can see some concerned faces when I say it absorbs in. It's a gas, so you add a lot of extra gas. That extra pressure pushes it into the fruit, and then when you vent it, you flush clean air through, it all comes back out. But in those experiments, we want to know what that concentration is over time. And those experiments, generally a long period of time, like some of them were 12 hours. And so we would measure every 4 hours to see what the concentration is. And from that, we could figure out how effective it was at killing the insects. So that would be an example of a long sampling time. Basically all of those were longer than an hour. One method you could use is polarimetry. You can actually do this with anything that's chiral. So if you've taken any biology classes, you've learned that there are enzymes and proteins and other molecules that are chiral, right? There's a left hand and a right hand motion. One of the really, really famous examples was, I forget what it was. Thalidomide. Thalidomide has two forms, basically a left-hand and a right-hand form. One of those forms was fine, really great. They used it to treat morning sickness, so the anti-nausea. The other form was, what is the correct word? It's like teratogenic, caused mutations in fetuses, in babies, which is really terrible if you're using this to treat morning sickness for women or people who are pregnant. Those molecules often rotate light. It's not used anymore. It hasn't been used for a long time. Those molecules will rotate light, and the amount that they rotate light depends on the concentration in the solution. So if you have a polarimeter, it can measure the amount. You'll have some standard that's like the light is pointed this way, essentially. You add in your sample, and the light is rotated 90 degrees. You measure it a little bit later, it'll be rotated less and less and less as that concentration gets used up, and there's less of that molecule rotating the light. You could also use total pressure. That does require a reaction where the pressure is going to change. No, we'll talk about this later. So like in this reaction, though, we've got dinitrogen monoxide reacting to be nitrogen and oxygen. The pressure changes because as the dinitrogen monoxide reacts, there's two gases or 2 moles of dinitrogen monoxide, and that becomes 3 moles of gas. So 2 moles becomes 3 moles. If this reaction is moving forward, the pressure in whatever it's reacting in is going to increase. If the reaction is moving backwards, then the pressure will decrease. So you could use that to measure the progress of the reaction. Or spectroscopy, which covers like a whole bunch of different methods, but usually is measuring the amount of a particular wavelength of light that gets absorbed. If you got more of that molecule, absorbs more light. And those are all, can be continuous, or don't necessarily have to be continuous. Periodic sampling. So here, it's measuring the iodine with a spectrometer. So you have some source of light. That light gets channeled through a prism or some other type of monochromator. So mono meaning one, and one color of light, essentially. That gets shown through the sample. We had to use these later. You use these in Chem 1? I don't think you use these in Chem 1. Yeah? We just taught Chem 1 last semester. I should remember that. No, right? Okay. We had to use it this semester. We'll use this to measure concentrations. And then it detects how much of that light there is, and so you can get that amount over time. Oh, we didn't get as far as I wanted to. Methods for periodic sampling. This is what we did for gases when we were doing post-harvest fumigations. You take out a sample of gas, you shoot it into an instrument, you measure the concentration. You come back later, you take out another sample of gas, shoot it into the instrument, and you get quantitative analysis. All of these you can get quantitative, but quantitative meaning it'll tell you the actual amount that's present. So you'll be doing titration. I don't know about gravimetric analysis. We won't be doing any gas chromatography, unfortunately. That's one of my favorites. But if you take OChem, you will. Do a lot. This is a gas chromatograph. You guys have done like TLC plates, or you've seen like the demonstration where you put like the dots on a piece of paper, and it, as the water, or you put the end in the water, as the water goes up, it separates out all the colors. This is doing that with gases. So you inject a gas sample, and it's got different affinities for that column. So as it flies through, some of them go faster, some of them go slower, and it separates things out before they get to the detector. So then you can just look at one thing at a time. Got a little time still. A reaction order. We might have to come back to this on Friday, but to introduce it, the rate law gives us a relationship between the reaction rate and the concentration of reactants. And this is as we're trying to kind of step from just having these average rates where we can say something about instantaneous points in time or a certain time period. This is how do we eventually predict what a reaction is going to do in the long term. And it turns out that we can take these reactions and we can put them into these categories that we call orders. So there's zero order, first order, second order, and beyond that, but we're going to talk about these three. And the order is N, which would be this part of the rate law. And there's also a constant for that rate law related to the specific reaction. So the order tells us is how does the reaction respond to changes in concentration of the reactants. So we saw from the graph earlier that as the reaction goes forward, the amount of reactant decreases. Makes sense? But the amount that it decreases by also decreases. So it slows down over time. It doesn't go in a straight line and then stop. It gradually decreases and gets slower and slower and slower. Well, it's not the case for every type of reaction. So a zero order reaction or process is independent of the concentration. So that means that that would be a straight line. It doesn't matter what the initial concentration is. The rate never changes. The most common one for this actually in terms of chemistry is radioactive decay. Radioactive decay is independent of the amount of substance. That's why we talk about radioactive decay in terms of half-lives. So how much does it take for half of it to go away? That's really all the information that you need. For first-order reactions, they are directly proportional to the concentration of A, or one of the reactants at least, meaning that if I decrease the concentration by half, the rate decreases by half. If I decrease it by a third, the rate decreases by a third. If it's a second order, it's proportional to the square of the concentration. And if you like math, you can tell by the way it is from the equation, right? If this exponent is 0, anything to the 0 power is 1. So the concentration of A disappears from the equation. If it's first order, then it just is the concentration of A that affects the reaction. If it's second order, then I'm squaring the concentration. And you can have third order, fourth order, and beyond. So looking at our graphs of the concentration versus time, see it's zero order, perfectly straight line. First order decreases, the rate decreases, or the concentration decreases, but also the rate decreases. And for the second order, that happens even faster. And then this one can be a little bit confusing. We're still talking about reactants, but this is the rate now as it relates to the concentration of A. So as I increase the concentration of A, for zero order, you can see no change. But the first order now is a straight line, increasing 1 to 1. So doubling from 0.2 to 0.4, the rate should double in that same space. And then for second order, it increases according to the square. So zero order again, because it's A to the 0th power, that becomes 1, so the rate is equal to K. So in a zero order reaction, K is the rate. Whatever that constant is the rate of the reaction. So like I said, radioactive half-lives, radioactive decay is zero order, but also something like sublimation is zero order. The concentration doesn't matter. It's just how long it takes for the outer layer to leave. Then the next layer can leave, dependent of the concentration. I guess it would be dependent on surface area, though. I like radioactive decay better. First order is where the rate is directly proportional to the concentration of the reactant. So again, it's 1 to 1. The exponent here is 1, so this concentration times the rate constant gives you the overall rate. And then the second order is proportional to the square. We're taking the concentration and squaring it. So that concentration has an even bigger effect on the overall rate. Oh, yeah, good. So close. Well, that clock's really slow. Okay, so we'll do this last question, and then on Friday we talk about determining the rate reaction order. So for a particular reaction in which A converted into products, doubling the concentration of A causes the reaction rate to double. What is the reaction order? What? B. 1. Yeah, B. Oh. What would have to happen for it to be a second order reaction? If I double the concentration of A,
Wait.
then it would be, well, yeah, C, but it would be 4 times. Yeah. All right. I'll see half of you tomorrow and the rest on Friday.
Yeah, the clock is very slow.